but we're going to get a lot more specific on it. We're going to talk about concavity for a little bit, and that's just whether, I'm sure you've talked about concavity before, like with lenses and stuff like that. You probably refracted light and reflected light and split light apart so it's different colors and stuff like that. So we're talking about concavity, and this makes sense. This would be concave down between points A and B, and this would be concave up between points A and B, right? Like, so the g of x function is concave up, the f of x function is concave down. So if you have the graph of the function, the curve of the function lies below the tangent line, it's concave down. And where would our point of tangency be? It would be here, right? And we'd be looking for that line. So if it's under the tangent line, we say it's concave down. If it is, my tangent line would be here on this one. If it's above the tangent line, then it would be concave up. I'm not sure why this is so fuzzy on my screen, but it looks okay up there. I have no idea. It's okay. If you're watching this video later, it's probably going to be a little bit fuzzy. Slopes it. I don't know. I think it's because I'm not running it like it's hooked right into my document camera. I don't really know what its problem is, but for some reason it's coming up fuzzy on my screen. But you're here live and in person, so we'll call it a win. Slopes of the tangent line increase from left to right as the tangent. So if we're talking about concave up, what do we know about these slopes? They're going to be negative, right? Because they're sloping down to the right. We're going to get a slope of 0 at the bottom, and then they're going to start to increase. So negative, negative, 0, and then positive, positive. So they're going to be increasing as the line moves to the right. Concave down is going to be the opposite of that. Your slopes would be positive, 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 then they're going to hit 0, and then they're going to come down from that. So what we know here is the first derivative and the second derivative are positive for concave up, and for concave down, the first derivative and the second derivative are both negative. That's super fuzzy on my screen. I'm going to try to get over it. So if the second derivative is greater than 0, so that's just saying it's positive, right? Like, so that's just saying it's positive. For all x on whatever interval we're happening on, then we'd say it's concave up over that particular interval. If the second derivative is negative, we know over an interval, whatever that interval is, we'd say it's concave down. So this is what we do. We use the critical values from the first derivative to separate the increasing and decreasing, which we've done before. So we're setting the first derivative equal to 0 to find our critical values. If you don't already remember that, because I don't know what lesson we did that in, but so we find the critical values by setting the first derivative equal to 0. So the zeros of the second derivative, the zeros, so that means we're solving the second derivative. So if we're solving the second derivative, we've got to set the second derivative equal to 0. And that will tell us where the concavity changes. Yep.
Why are we setting the first derivative equal to 0? Like, why are we finding
Critical values? Oh, sorry, we're going to be graphing polynomial functions. So we need to know where our relative max and mins are, right? So in grade 12 pre-cal, we knew where our x-intercepts is. First derivative is going to give us critical values, which will be our absolute or relative max or mins. So that's what that one does. The second derivative, when we solve the second derivative, it's going to tell us the point, it's called an inflection point, where we kind of switch directions, where we go from concave up to concave down.
what
So,
way we curve the graph?
yes, exactly. Yeah, that's a great way of putting it. And so this is going to give us the points where the concavity changes, and we call that the point of inflection. Okay. Flipping the page. So I got a graph right here. So what I've labeled is my, like you see the lines on it, those are like points of tangency. So even without doing any math, what kind of slope is this line right here? Is it positive or negative? It's positive because it's rising to the right. So we know that the slope is positive. Okay? So we know that, what's the slope here on the horizontal line? It'd be 0, so the slope is 0, and we know on this side that because it's falling to the right, the slope is negative. So that's all grade 10 stuff, but it's good to remind ourselves what's happening there. So if we look at the interval from -5 to -1, so we're looking at this point, that section of the graph, we're going to say it's concave down, because there's my real point of tangency, that's a relative max, and the graph happens under it, so it's a concavity down. If we look at -1 to +1, I'm just going to grab a different color here, -1 to +1, we know that this has negative slopes, a 0 slope, and then a positive slope. We also know that the graph is occurring above that 0 slope, so it's concaving up. And then again, from 1 to 3, trying to grab different highlighters here, 1 to 3, it's up. And all of this is pretty you look at the graph and you're like, duh, it is up. And then we have the interval from 3 to 5, and that goes back to concave down. So different sections of the graph. So when we're talking about the interval, we're talking about sections of the graph. Because if we looked at the whole thing all together, we couldn't say because it's both up and down. So we're going to break it into obvious intervals. And if you notice, none of the intervals have any inclusion points. Because when we're looking at -5, that's a 0. It's neither positive or negative at that point. So we're looking at what's happening in between them, but not including those points. So just keep that in mind. Okay, here we go. Determine the concave up and concave down intervals and any points of inflection for the function. So points of inflection happen in the second derivative, when we set that second derivative equal to 0. All right, so if we're talking about a point of inflection, a POI or an IP, inflection point, sometimes I do it backwards, we're going to be looking at setting that second derivative equal to 0. Sorry, we're not equaling it to 0, we're solving it. Sorry, not equal to 0. But it does deal with the second derivative. It's not equal to 0. We're not solving it. We're solving it for the critical point. Let me go back and change that on the Beth. So we're going to substitute in the critical point in for x. And we've done that already. Sorry.
So the equal sign stays.
It doesn't have to. Look at that. So you got an eraser. You're all good. Okay, back to this. All right. So determine concave up, concave down. So the first thing I have to do is I have to find my critical values. I don't know if there's more than one. And how we're going to do that is the first derivative. I like to figure out what my first derivative is first before I go ahead and solve it. It just makes more sense to me. You know what, guys? You do set it equal to 0. I was right. My brain's functioning slowly. You do set the second derivative equal to 0. So,
That's what I said, the equal sign stays.
well, it equals 0, so we can go back and put that equals 0 in there. So we are going to find the second derivative from this. We're going to find the second derivative right away. Ooh, I'm bouncing all over the place here. So that's going to be 12x plus 18. Okay, so to find, let's go back to that little note there. So to find, so the zeros of the second derivative will indicate where the concavity changes, and that's your point of inflection. So we are going to set it equal to 0, and we're going to find that point of inflection. So we're going to take our second derivative here, and we're going to find our point of inflection. So 0 equals 12x plus 18, so negative 18 equals 12x divided by 12. Divided by 12. If I take 6 out of both of those, I'm going to be left with a negative 3 over 2. So negative 1.5 if we don't want to use fractions. So that's your point of inflection.
Stuff like the vertex.
Kind of, yeah. That's a good way to put it. It's a change direction point. Okay. So I have the x value. How do I find the y value? Into the original. Into the original. So step 1, we're finding our second derivative, and we're setting our second derivative equal to 0 to find our point of inflection. We need the coordinate pair, so we're going to substitute negative 1.5 right back into that original equation. So no derivatives, just the regular . Ooh, I'm right off the page there.
You get 8.
Did you get something different, Rahat?
No.
All right, so now that we have the actual point of inflection that we would graph on the actual graph, we're going to see which way things are going. Is it is it a relative maximum or is it a relative minimum? So we're going to look at which way the line curves to that point. So now we're going to do just a sign analysis, and we're doing a sign analysis off the second derivative. So I only have one point of inflection. So I know there's only, well, I guess it would be an absolute max or an absolute min, because there's not more than one. So we're going to look at this, and we're going to substitute some values in. What's a value to the left of negative 1.5?
Negative 10.
Let's go negative 2. Let's not use big numbers for half.
Well, then that we could just like easy math.
But this is easy math. So I'm going to substitute that into here. So I'm going to have negative 24 plus 18. Is my answer going to be positive or negative? Negative. And we'll pick a value greater than negative 1.5.
0.
Okay, 0 is a gooder. So this one's going to be positive. Didn't even.
That means it's a relative minimum.
Okay, so let's think about that,
So
right?
concave is going
So
up.
we're down, 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 and then we're going up, up, up. So we are at a relative min. So what we know about the graph is that the graph, the original graph, f of x, what's the interval that f of x is concave down over what?
Negative infinity to negative 1.5, not inclusive.
Not inclusive. And then f of x is concave up over the interval to positive infinity. Now we would have different ones if we had multiple points of inflection. Okay? Fun times.
Sound conveniently, our R is coming like this till negative 1.5, and after that it's going back up, right?
Mhm. So, but what's the original function? It's a
Oh.
cubic, right?
Oh, right.
So it's gonna start in 1 and end in 3.
Mm-hmm.
So we might have a bump in there somewhere, but we will have the end values go off to infinities, right? Okay, so here's the tough stuff. Well, not really the tough stuff. It's just a lot. Like when you're sketching a polynomial graph, we're going to do a couple of things. We're going to sketch the y-intercepts, the x-intercepts. That's grade 12. Like that's pre-cal. And then all this stuff is stuff we've done in calculus. So this is all the calc stuff. So our job in grade 12 was to learn the end behaviors, whether it's like what the positive and negative leading coefficients did, how to do synthetic division. Now that you know how to do that, I expect you to do all of that and all of this stuff. So let's synthetically divide this one. So this is a refresher from pre-cal, which we just did, so it's not too much of a refresher. It's just chapter 3. We will leave out the other word, but we will just say it's just chapter 3. So if I want to solve this, I'm looking at the factors of negative 6 that give me a remainder of 0. And what do I know about this?
That's not gonna work
Pardon? What? What do I know about it? We're probably going to need a negative x. Like all of these are positive. So if I put a positive number in there, I'm going to have a bigger positive than I will the minus 6, right? So I know I should start with negative numbers. And we know that we've got plus minus 1, plus minus 6, and then we have plus minus 2 and plus minus 3. So we know those are all the factors of 6, but we just made the smart decision that we should probably pick a negative number. Does negative 1 work?
No.
No, it doesn't. That's sad. That's sad. Does negative 2 work?
Negative 2 does work.
Does work? Okay. So what do we know?
Let's chug it into the function. Box.
Okay, we check it into the box. Yeah. So what are we checking into the box?
297 -6.
Okay, so inside the box is going to be 2, 9, 7, -6. What has to happen to these, or I guess what has to happen to this function here? Has to be in ascending order based on exponents. And if you're missing any exponents, you got to put a 0 in. Okay? And then what's the number outside?
-2. Oh, yeah.
We prove that it has a remainder of 0. You can do it both ways, but we're subtracting. We did the subtracting one. It'd be -2 on the outside.
The factor is x plus 2, but
Right, so the factor
Yeah.
would be x plus 2.
Yeah, that's what.
But we solve it, so we're using the -2. So 2 goes down here, and then 2 times that is -4, and we are adding, so this will be 5, that'll be -10, that'll be -3, and then that will be 6, and that will be 0. You know you've done it right if this is 0 and that's 0. Because that's my remainder, that's my constant, that's my x squared. So we're going to have 2x squared plus 5x minus 3. And what can we do here? We can factor this one because we're looking 2 times 3 is -6. -6 factors that add up to
6,
5 would be
-1.
6 and -1.
it's scary. If one thing goes wrong at the starting, the whole answer would be wrong and the graph would be off.
Pascalian for physics, I got everything right.
It's like, you
I
know,
only screwed up one question because I forgot gravity.
it's like one question, like of 100 marks and full exam.
Yeah. So there's my, and I just took this one from up here and I brought it down. Those are all my factors. So if I were to set my equation equal to 0, we know that our x-intercepts occur at +1/2, -3, and -2. Where's my y-intercept? And I got that from the original. If I were to put zeros in for all the x's here, I get -6. Okay, some other things to remember from domain and range. The domain of a polynomial function is always XER. It's always -infinity to +infinity. Doesn't matter if it's an odd or even degree. The range definitely depends on the degree of the function. Odd degrees, they will be -infinity to +infinity. Even degrees with a positive coefficient are going to have that minimum value and goes on forever. If they have a negative leading coefficient, it's going to have a maximum value and the bottom will go on forever and ever. So that was your chapter 3 in a nutshell. Okay, this one's super easy. It's giving you all the points. So we are going to sketch it. Are we ready? I believe this is the... So if you guys noticed the first example, we did the inflection points and then we used that same one to find the x-intercepts. So now we're putting all the points on the graph. So it's just all the math we just did. So relative minimums and relative maximums, we didn't actually calculate these. These are from your first derivative. So if you're wondering where those are coming from, we solve those from our first derivative. And I'm just going to flip back for a second. Our first derivative was a squared, so we ended up with 2 values if we were to factor it, which we didn't because we didn't have time, but that's where those are coming from. We know the y-intercept is 6. We know the x-intercepts are these, which we just found. We found the inflection point, -1 and -3. We know where it's concave up. We know its domain and range. So all we're doing is plotting these points on a graph. All right, here we go. Easy peasy. Okay, everything on this side, we're plotting. Everything on this side, we're just checking or using it to confirm that our graph looks right. So anything on this side, we're just confirming. All right, so FYI, there's my -1, there's my +1. It's like, it's kind of hard to see when, so it's 2 ticks over, and like that's 1, that's 3. I find it hard to always see them, like I gotta count them out. It just helps my brain. Okay, so we're -0.5, so right here, and -7.5. So there's 7. And there's 7.5. So that's my relative minimum. My relative maximum is at, so there's -1, there's that's -2, -3, -4, -5, -6. So I'm going negative, so -2, -2.5, 1.5. So there's my relative maximum. My y-intercept crosses at -6. My x-intercepts are at -2, -3, and +0.5. Okay, so I'm going to connect all those points. So I know that my leading coefficient was positive, so I should be in 1 and 3. My end behavior is in 1 and ends in 3, which is good. I'm easily able to hit all of those points. So that's my good looking graph. Okay, are we ready to keep going? I'm going to flip, and we're going to go through graphing a whole polynomial function, like from start to finish. So I would say let's start in grade 12 pre-cal. So grade 12 pre-cal is I'm going to find my x-intercepts first. So I'm going to start my x-intercepts. When I'm looking at this function, what do I know? It is even. It's a positive coefficient. So I know that it's going to open up and it's going to have a minimum. So my end behavior is going to be in quadrants 1 and quadrants 2. When I say opening up, this is the end behavior that I'm referring to. Okay. X-intercepts, what do I gotta do first? Does it matter? Should I be checking positive or negatives, anything like that? Is there anything that will help me in this one? So plus minus 1, plus minus 4, plus minus 2, plus minus 2. Will 1 work? Yeah, 1's gonna work. All right, so here we go. So we know it's that. Ooh, that's a little ugly. Okay, so we're gonna do one. My pen's drying out here. Okay, what's going inside the box? 1?
1, 0, negative 5, positive 4.
1 more 0. Right, because we're missing the x too. We're missing the x cubed and we're missing just the single x. All right, carry down the 1. 1 times 1 is 1. And we are adding, I always like to write that in. All right. So remainder constant x squared, x cubed. Whew. So we have x cubed plus x squared minus 4x minus 4. What do we need to do here? We need to go again, right? Do it again. What's going to work? Two would work?
Yeah, 2 works.
2 works, so we're going to have 2 cubed plus 2 squared minus 4 times 2 minus 4. So we're going to have 8 plus 4 minus 8 minus 4. So that works. So here we go again.
The factor is going to be x minus 2.
Okay, so we have all of them this time. So that's nice, at least. So we don't have to accidentally make a mistake there. What did I do wrong, guys? Oh, because it's a positive 2. Silly me. All right, so we know that this factor is going to be x minus 2. So we're going to be left with a constant, an x, and an x squared. So we have x squared plus 3x plus 2. And I think we can factor that.
X plus 2, x plus
Oh my goodness. That has taken up a lot. So what are all the x-intercepts? X equals negative 2, x equals negative 1, x equals positive 1, x equals 2. We may need a second scrap piece of paper to do the rest of our math on. That took us a little while. What's our y-intercept? Okay, so now we're gonna find our, sorry, is it positive 4? Now we're gonna go and head ahead and find our relative max, or min, but what did we say we were gonna have? We're definitely gonna have an absolute min for sure, because it's a even function opening up, so there will be an absolute min, but we gotta find some critical values. So we have to do the relative or absolute, depending, I always just call them relative, because some will be max, some are absolute. But that's related to our first derivative. So I'm gonna solve for our first derivative, which is 4x cubed minus 10x. And we're going to set that equal to 0. I'm going to take a 2x out, so I'm left with x squared minus 5. Oops, sorry, there should be a 2 in there. Do you want to do sign analysis, or do you want to do second derivative to figure out if these are max or mins? Second derivatives. Okay, so we have 3 critical values at 0 and then at the plus minus 5 root 2. And FYI, that's approximately 1.58, just in case you're like, because we're going to graph them, so we're
Find the second derivative by using critical values, or can we directly do the inflection ones? Because if it tells us it's going to give up one down, and we can just do it now. Is there a shortcut? Maybe. Inflection point will tell us where it's changing.
yeah, but it might change. It might change on, because we have so many of them. I don't know if it will be as obvious as before. So I'd like to do second derivative to just confirm that they're maxes and mins, and then we'll go from there. So we're going to use, so is it, a max or min? We're going to use the second level derivative for that. And the second level derivative is, where's my first derivative? Is down here, so it's going to be 12x squared minus 10. I think I did that right. Yes, I did. And so what do we do with this when we're doing second derivative? Do we set it equal to 0 and solve, or what do we do? We substitute those critical values in. So our first one is going to be 0. So our second derivative, or sorry, our second level derivative. So we know that at 0, it's going to be a maximum, right? Because we get that negative 10. Remember that the second derivative rules are opposite to what you think they are. So then we're going to go for the second one. I'll do the positive 1.58 first. Or I guess, you know what? I could probably use the actual root, because there's a squared in there, and that will save me some time. What do you know right away without doing any math? What do you know the negative root? It's gonna, no, it's gonna be a minimum. Yes, it's gonna be a minimum as well. I don't think we need to show the math for that one. Is everybody okay if we don't do that? Because if I substitute a negative root 5 over 2 in here, when I square it, it's gonna be the exact same answer. So we know that x at negative root 5 over 2 is a min. Holy Hannah. Okay. So now you see the added thing that we did in calculus that we don't do in pre-cal. This is just that extra piece there. Okay, so now we're going to do our point of inflection. So we're going to do our point of inflection, or maybe it's points. I'm not sure if it's multiple or just one. So we're going to take our second level derivative, which I found up top there, and we're going to set that equal to 0, and we're going to solve it. And that is, if you actually, like if you make it a decimal, that's what it is as a decimal. So we have 2 of these. So if we were to pick points around them or in between them, if we were to substitute 0 into the derivative, what would we get? We get negative, right? Because we're putting 0 into there, so we would get a negative, Rahat. If we were to put 1 in there, we would get a positive. And if we were to put a negative 1 in there, we would also get a positive. And again, we're not worried about the numbers. We're just actually worried about where that concavity is changing. Now, the point of concavity is going to be about where our graph is curving up and where it's curving down. So when we graph it, it's going to look a little bit different. So if we find the points of inflection, so if we were to find the point of inflection, I have the x value, which is 0.91. No, that's negative 0.91 at this point. How do I find the y value into the original? You guys trust me? Because I did the math already.
Let's go.
Take one full period to do the test. I think so. So long.
So we, in order to get this, we need to sub into original. So just in case you forget what you're doing, you're subbing into the original. So all of a sudden, we've added so many more points to graph that we did in grade 12. Like grade 12, we did the basics, just to kind of get the feel of it, and now we're getting super specific. Okay, so if you guys have all that down, we're going to plot all these points. So really what we care about the x-intercepts, we care about the y-intercept, we care about our absolute max, or our relative and absolute max and mins. This graph will have no absolute max, but it will have absolute minimums. All right, so here we go. You know what we didn't do? Is we didn't get the y coordinates for these points. We don't actually know where these points are. That would be kind of important.
Wait, but when x equals 0, we know y is going to be plus 4.
Perfect, we know 1. So we know x is a max, so that point you're telling me is 0 and 4. And what's this point? So we know, we didn't find the y's on these ones. So this one is, what did I say? It was 1.58, so 1.58 is the x value. Do you trust me for the y value? No? Whew, we almost tried to graph stuff with only an x value. That wouldn't be good. And how did I find these? How did I find that? I'm subbing back into original. Okay, let's plot all the points. I got -2. I have -1. I have +1, and I have +2. Rad. Have you finished graphing? You have? Oh, my apologies, sir. My apologies. Okay, 0 and 4 was graphed, because that was my y-intercept. And now I have -1. So -1.58 and -2.25. So I'm like right there. 5, 8. So it's not exactly perfect. And we anticipated our end behaviors were going to be in 1 and 4. Now we had some points of inflection in there as well. We had -1.91, which is really close, and a half, which is that point on the line, and then almost 1. So they seem a little odd, the points of inflection, because they're on a straight, all the slopes are rising up, it's going to be positive, but this is coming off being a concave down, and then a concave up, and then this is where it starts becoming a concave down. So that's what the points of inflection are telling us. This is the point, that 0.91, I think that's what it was, 0.91, is where we stop being a concave up and start into our concave down. And that's where we finish being in the concave down and start into our concave up. It's a lot of stuff. It's not terrible, but it's a lot. So maybe we need to make a cheat sheet when we're gonna graph one of these, because this will definitely be on your test and it will definitely be on your quiz to do a full graph like this.